Hey ChemExcel. All right, we are at the point in the year where we're going to start answering a question that you've hopefully thought of at some point during the year, which is why do chemical reactions happen at all? Right? What drives a reaction forward? Right? What are the forces that say when you mix these two things together, something should happen? But if you mix these other two things together, nothing's going to happen. Turns out there's two factors that can drive chemical reactions. And there's some very interesting outcomes from this because the two factors could both agree that a reaction should proceed forward and it should happen when you mix those things together, and it will. Or both of them could agree that this is a bad idea and the reaction's not going to happen. But there's also the third outcome where they might disagree with one another. One of the forces can say, hey, it should go forward, and the other one should say, no, I don't think so. That's a bad idea. And in that case, you don't necessarily know offhand who's going to win. And even in that case, that's not really clear cut. There may not be a clear winner, or it could be that one of them wins at a high temperature and the other one wins at a low temperature. All right, so before we get into all of that, all right, which is really cool, we're just going to focus on the first driving force. And you already know what it is. It's enthalpy. You're familiar with it, but we have to start thinking about it in a slightly different point of view. Okay. So first off, a little refresher, right? We've seen exothermic, we've seen endothermic, all right? We know what kinds of things we're looking for to identify that. We're looking for the location, right, of the word heat or energy, or the actual amount here. So we know exothermic looks like writing that stuff on the products. Endothermic looks like writing it on the reactants. We also know that it could be written off to the side. You could have this delta H value, right? In that case, you can't look at the reaction and go, oh, it's a reactant or a product, and you have to look at the sign of the delta H value, right? If it's negative, that's exothermic, and if it's positive, then it's endothermic. All right, so that's things we're already aware of. In terms of what nature favors, okay, as you can see from this slightly horrifying image of a forest fire here, right, nature favors exothermic reactions, right? We know things burn really well, all right? Combustion reactions are a great example of exothermic reactions. And it's not that hard to get things to burn, right? So producing lots of energy is the favored option here. All right, so if we take a look at this reaction, we have a couple of hydrogen react with an oxygen to make some water molecules and energy. It's exothermic, all right? This would be favored by nature. And you may have noticed in the energy diagrams video, I briefly mentioned that some reactions can be run in reverse. So if we think about combining hydrogen and oxygen, all right, it's a very easy reaction. You have a balloon of hydrogen, which I'm sure everybody has, right? But it takes almost no effort. You just have to get a heat source near it and you can get a fireball out of that. All right, and I'll link these videos in Canvas too if you want to be able to watch the videos, all right, of the fireballs. They're fun. But we can also run this reaction backwards, okay? If we take the water and we add energy to it, we can produce the hydrogen and the oxygen. One way to do that is to run electricity through water. You need some dissolved ions in there to help the electricity flow, all right? And you can actually watch, like you can do this at home, like do this outside, okay? And please don't try to create a fireball out of your hydrogen and oxygen. You're gonna be there a while trying to collect that hydrogen anyway. But that's a pretty cool video. I'll link that too. All right, as you can see here, we're just using a standard 9-volt battery, right? And that's actually enough energy to decompose the water. And it does mention down here a little question of, can you identify which tube contains the hydrogen, which contains the oxygen? And we can, because we know that you get twice as much hydrogen as you do oxygen. So this one here must have the hydrogen, right? Because there's a lot more gas, like twice as much gas being produced there. So we have this reaction that normally occurs in the forward direction, all right? That's its natural exothermic way, but we can reverse the reaction if we put energy into it, okay? So this gives us a new way of thinking about things as like the forward and reverse, okay? Rather than just thinking about the forward direction, how we would classify that. All right, so I already mentioned this. In this example, right, the forward reaction was favored by nature because the forward one is the exothermic direction. Right? Forward reaction is the exothermic direction there. All right, that's in this example. That won't be in every example. Sometimes it's the reverse reaction that is exothermic. All right, so that's where we have to kind of get to that new way of thinking. Rather than saying, okay, this is what exothermic and endothermic look like, we want to think about it as this is what exothermic looks like if the forward reaction is exothermic, and this is what it looks like when the reverse reaction is exothermic. Okay, so that right there, that's that new way of thinking about it. Is now instead of endothermic, we're going to forget about that word and we're going to think, hey, these reactions are exothermic if you run them in reverse. Okay. So I'm going to give you a moment to try that. I want you to look at the examples, all right? Use that little guide, the summary chart at the top there, and determine which direction, the forward or the reverse, is the exothermic direction and therefore would be the direction favored by nature. Okay, just give you a moment to look at that. If you need more time, go ahead and pause the video and then unpause it when you're ready to move on. Okay, and answers. All right, so at this point, if you're getting something wrong and you're checking the chart at the top and you don't see why you had the wrong answer, all right, this might be a good time to just pause the video, email me, all right, and then continue on once you get an answer to your question, okay? All right, now my next question is, did you at any point stop to wonder why exothermic is favored by nature? Like, we know things burn really easily, but why? Right? Why is that the favored condition? And the answer has actually been hiding in your energy diagrams. All right, if you remember, we have 3 points on energy diagrams. We have the reactants, the activated complex, and the products. All right, the point with the lowest energy is the most stable point on that graph. It represents the most stable molecules. The analogy for that is that laying on the floor, which would be very low energy, is more stable than standing, which is high energy, because you can't fall over if you're already laying on the floor. All right, you're more stable that way. I'm sure some of you are going to go ahead and try to figure out how to fall over while laying on the floor. All right, let me know if you succeed. Those videos are, I'm sure, going to be entertaining. Okay. But if we take a look at these energy diagrams, I want you to take a moment and instead of thinking exo-endo, I want you to label one of them as exo-forward, one of them as exo-reverse, and then identify the most stable part of the diagram. And the most stable point would be the lowest energy. So I'll give you a moment for that. Okay. Okay. Pause the video if you need another minute. And I'm going to move on to the answer key. Okay. So this is our traditional exothermic one on the left here. Normally we would have called the right diagram endothermic, but now we're saying if this reaction ran backwards, it would be exothermic. It would have a drop in energy. All right, and we notice that, all right, hopefully you've noticed, right, is that exo forward means we end with the more stable substance in the forward direction. Exo reverse, we're ending with the more stable substance in the reverse direction. Okay. So when we say the driving factor here is enthalpy, really we're looking at molecular stability. All right, like water molecules are super stable molecules, but hydrogen and oxygen molecules themselves are not as stable. So they would favor forming water molecules, and it would resist breaking down the water into the hydrogen and oxygen. Right? Things decompose in nature, right? Unlike water molecules, but logs decompose, all sorts of things decompose naturally. But that's because they're made of all sorts of large, unstable molecules, right? Plants grow by using energy from the sun to create these larger, less stable molecules. So when the plant dies, those molecules are going to decompose into more stable things. Right, so that's really what it's about. It's all about the stability of the individual molecules. Right? If you have really stable molecules, they're going to want to stay that way, and they're going to resist changing. But unstable molecules are going to be much more reactive, right? And are going to produce those exothermic reactions to release that energy and form something more stable. All right, so now I want you to go to the worksheet labeled Factors That Determine Equilibrium. And you're going to just complete the first column, okay, just the first column, because the two driving forces are completely unrelated to one another. So go ahead and practice them in isolation first, all right? Go practice with the forward and reverse thinking about your enthalpy instead of the exo and the endo, and then check it and let me know if you've got any questions.